All right, welcome everyone. Whether you're a newly onboarded intern hitting the lab floor for the very first time or an executive stakeholder dialing in from the boardroom, I am thrilled to have you here for this high-stakes explainer on our global technical standards. I'll be acting as your lead scientist today, and we're going to look at chemistry a bit differently. We're not just looking at it as a science, but as a formal communication protocol. And let me tell you, mastering this protocol is absolutely non-negotiable for operating safely and effectively on a global scale.
So, here is our game plan for today's structured onboarding curriculum, which is designed to make you totally fluent in this universal language and ultimately secure our global supply chain. We'll quickly run through the universal chemical alphabet, look at formula architecture, dive into stoichiometric auditing, explore the taxonomy of chemical reactions, and then we'll wrap it all up with a rapid-fire certification quiz. Let's get moving.
Starting right off with Section 1, the Universal Chemical Alphabet Protocol. Let's transition from abstract theory to the absolute rigid precision we require in our international procurement contracts.
Here's the thing. You have to start viewing chemistry as a formal language protocol. If we're going to communicate with absolute fidelity from a lab in Berlin to a manufacturing plant in Tokyo, we need ironclad rules. Think of it like this. Our chemical symbols are our letters. When you combine those letters, they form formulae, which act as our chemical words. And finally, these words interact to form complete chemical sentences, which we call equations. Those equations give us a highly precise narrative of physical change.
Now, a chemical symbol? It's definitely not just a handy abbreviation or a nickname. Think of it as a highly dense data packet. When you write Fe for iron or O for oxygen, you are instantly communicating three absolutely critical things: the immutable identity of the element, an exact count of precisely one atom, and a definitive mass quantity. Having that level of granularity is literally essential for scalable manufacturing and making sure our contracts are mathematically perfect.
And this brings us to the Latin anchors. You might wonder, why Latin? Well, imagine the absolute chaos if a multilingual supply chain gets confused because one lab's sodium is another lab's natrium. To prevent those catastrophic disasters, we rely on strategic historical routes that completely bypass modern linguistic shifts. Globally, we anchor sodium to the Latin natrium, which gives us the fixed symbol Na. Iron is anchored to ferrum, giving us Fe. This historical standard ensures that a symbol on a procurement order means exactly the same thing everywhere on Earth. Moving right along to Section 2, Valency and Formula Architecture. Let's see how this syntax translates those individual elemental letters into stable chemical words.
Because, frankly, atoms don't just mash together randomly. They are strictly governed by something called valency. You can think of valency as the master key of our chemical syntax. It represents an element's combining power, basically how many electrons an atom needs to gain, lose, or share to reach ultimate stability. By strictly enforcing these mathematical rules of atomic bonding, valency is what prevents us from creating chemical gibberish.
So how do we actually build these chemical words? We use what's called the crossover method. It's basically a mathematical handshake that guarantees the structural integrity and electrical neutrality of every single compound we make. First, you align the symbols side by side. Then, assign their valencies at the top, and literally cross those values down so they become the subscripts of the opposite element. Finally, we polish the notation by dropping the number 1 since it's just implied. It is such an elegant, foolproof system for constructing stable matter.
Now let's talk about how we visualize these bonds, because it changes depending on the data you need. An empirical formula kind of zooms out, giving us the absolute simplest, stripped-down whole number ratio, like CH2O. A molecular formula tells us the actual physical number of atoms in the molecule, like C6H12O6 for glucose. But a structural formula, like a spatial map of methane, gives you the exact spatial architecture and physical branching of those bonds. It shows how chemists have to adapt their notation based on the specific granularity required.
All right, Section 3, Stoichiometric Auditing of Equations. Now that we're scaling up to complete chemical sentences, we have to face the rigorous process of verifying our work.
When we balance an equation, we aren't just doing math. We are performing a strict, rigorous audit of matter. Thanks to the law of conservation of mass, atoms are never just created or destroyed. So an unbalanced equation isn't just a minor typo. It literally represents unaccounted for matter or energy. In our industry, that translates directly to massive operational liability and severe safety risks. We literally have to balance the books of the universe.
So, here is a vital reminder for everyone logging reports. There are strict notation rules you simply have to follow to avoid massive errors. Always capitalize the primary initial and use a lowercase for the second letter. When you're auditing and balancing, only use front coefficients, those big numbers at the very start of a formula. And please, listen closely. Never, ever alter an internal subscript to balance an equation. Changing an internal subscript alters the physical reality of the molecule itself. Doing that voids global contracts, plain and simple.
Which brings us to Section 4, Taxonomy of Chemical Reactions. Let's step out of the written equations and into the physical reality of the lab to analyze the real industrial risks involved.
Okay, we really need to highlight the aqueous state here, often written as AQ. Logging these state symbols is completely non-negotiable for actionable lab conditions. Why? Because the aqueous state acts as a catalyst, breaking atoms out of their rigid lattice entrapment. If you mix two dry solid powders together, absolutely nothing happens, because those atoms are locked in a cage. But dissolve them in water, it frees those ions. It gives them the physical mobility they need to actually collide, interact, and react.
Just visually imagine all these freed atoms rearranging themselves. In combination reactions, they merge to build anew. In decomposition, they shatter apart. But the industrial risk really spikes in the other two types. Neutralization reactions, where acids and bases swap to form salt and water, bring intense exothermic heat that demands advanced cooling systems. And displacement reactions, where a highly reactive element bullies its way in and forces out a weaker one, while those require strict predictive reactivity control and blast shield protocols to stop runaway reactions.
Okay, Section 5. It's time for our rapid-fire certification quiz. Execs, interns, get ready for a high-energy lightning round. Let's review the 10 essential study guide questions to certify your fluency in this standard. Let's go.
Questions 1 and 2. What are the communication objectives, and why the Latin anchor? Well, universality, precision, brevity, and global comprehension are our core goals, and the Latin anchor securely prevents modern, multilingual procurement errors by fixing historical roots to our symbols. Moving to question 3. Why do we call a symbol a data packet? Because it instantly gives us the identity of the element, exactly one atom's count, and a definitive mass quantity. That is the exact data required for true industrial scalability.
Question 4. Empirical versus molecular formula. The empirical view is your simplest, stripped-down whole number ratio of elements. The molecular view, on the other hand, shows the actual physical number of atoms present in one complete molecule.
Questions 5 and 6. What is valency, and what's the crossover method? Valency is the combining power. It's the master key for stability. And the crossover is our mathematical handshake. Align the symbols, assign the valencies, and cross those values down into stable subscripts.
Question 7. Radicals versus ions. An ion is broadly just any electrically charged entity, positive or negative. A radical is a very specific polyatomic group of atoms that carry a net charge and function entirely together as a single reactive unit. Question 8. Why is an unbalanced equation a severe operational liability? Because it violates the strict law of conservation of mass. Atoms are never destroyed, so an unbalanced equation literally represents unaccounted for mass or energy.
And finally, questions 9 and 10. Lattice entrapment prevents solid reactions by locking atoms in place until the aqueous state frees them to collide. And for neutralization, the absolute primary risk is managing that sudden extreme exothermic heat safely. So, to wrap this all up, mastery of this protocol is the absolute prerequisite for universal fluency. You aren't just writing letters on a page here. You are commanding the very architecture of matter itself. Thank you all for joining this explainer today. I want to leave you with one final thought. If we can master the syntax of atoms to accurately build anything on Earth today, what entirely new elements and compounds might we write into existence tomorrow?